Hello students, in today's lecture of Unit 3, we will discuss two important topics. One is the fuzzy graph and another is the tolerance and equivalence properties of a relation. First, first of all, we will study the tolerance and equivalence relations property in the context of crisp relation, and then further we'll conceive the same idea and establishing the similar kind of properties in fuzzy relations. So let's come on the first topic, that is the fuzzy graph. So suppose we are having a binary fuzzy relationship. So that binary fuzzy relationship can be represented in the form of graph also. So that graph is known as fuzzy graph. So we can say that fuzzy graph is a graphical representation of binary fuzzy relations. Binary means when we are having a relationship between two fuzzy sets, and their relations can be like that. Suppose we are having a single one fuzzy set, and the members of the same fuzzy sets are related to the other members of the same fuzzy set. In that way we can also establish a kind of relationship, and that relationship is also known as the binary relationship. So here the space is x cross x, and we may have a different kind of scenario where we are having two different universe of discourse, and there is a mapping between the element of the first universe with all the elements of the other universe. So that kind of mapping, that kind of relationship is also known as the binary fuzzy relationship. So we are saying that a fuzzy graph is the graphical representation of the binary fuzzy relations. So here, because we are talking about the graph, so certainly in a graph we know that there are two things. One is a set of nodes, another is a set of edges, rather we can say set of arcs. So here the elements of the universe of discourse, they will represent the nodes, and the membership and the relationship between the ordered pair of these elements, they will represent the arc of the fuzzy graph. Like, just see here, say for example, the here each element of x and y, here x is a fuzzy set, y is a fuzzy set. So each element of fuzzy set x and fuzzy set y, they corresponds to a node of the fuzzy graph. And on the other hand, the links between the elements of universe of discourse x with the universe of y, these links, they will represent the arcs, and we will label something on the arc, and that will be the membership value of the relation. So here we are saying the links are present in the form of arcs, and these links are labeled with the membership value mu r xi yj. Say for example, in the relation which is the basically the Cartesian product of two fuzzy sets x and y. Say for example, the ordered pair of xi yj, it bears a membership value, something, it may be anything. So that value will be marked as a label on the arc which is connecting node xi to node yj, right? Now suppose if these two fuzzy sets are not different, they are not different, x is not equal to y, it means suppose they are different, x is not equal to y, they are the different sets, they are the different fuzzy sets, then in that case the links connecting to two nodes is an undirected binary graph, and this is called the biparate graph. And suppose there can be another criteria where x and y, it means we are saying that the two fuzzy sets are same, we are saying that two fuzzy sets are same, and in this scenario, if two fuzzy sets are same, we are saying that the elements of the first graph, the elements of the first set are connected to the elements of the same set. In that type of scenario, the fuzzy graph is called the directed graph, right? Now see here, I'm taking an example that we are having a universe of discourse, and in the universe x there are four elements. There are four elements, and we are making a relationship with x and x itself. So the space is x cross x. So each and every element is having some kind of relationship with the other elements also, and that relationship is mentioned in this matrix. That relationship is mentioned in this matrix. It shows that x1 is related to x1 with the membership value 0.2, x1 is not related to x2, it is related to x3 with the membership value 0.5, it is not related to x4 at all, like this. So it means we are having a relationship on x cross x. So for that one, we are representing it with this fuzzy graph. We are having the fuzzy graph like this. Here x1 is having an arc which is connecting to x1, and the label is 0.2. It is representing the membership value of ordered pair x1 x1. Here it is having an arc which is directed from x1 to x3, from x1 to x3, and the membership value is 0.5. So here we labeled it with the R. In the same way, we are representing the information, and this type of representation is known as the fuzzy graph, right? So now let us take another example. Suppose we are having two fuzzy sets, and these two fuzzy sets over these two fuzzy sets, we established a relation, that is the fuzzy relationship R, and say the fuzzy relationship is mentioned like this. It's a set, it's basically a set, and here we have seen that some of the ordered pair are there, and their membership values are mentioned here. Their membership values are mentioned here. It is mentioned that there is a relationship of x1 with y3 with the membership value of 0.2. Similarly, x1 is related to y2 with the membership value 0.4, and rest of the ordered pair which are not mentioned in this relation, they are not at all, they are not related to each other at all. So we maintain a matrix here of the relationship. You can see here x1 y1, because x1 y1 is not mentioned here, so there is no relationship. That relationship is mentioned here with the membership value 0, then 0.4, then 0.2. You can see here x1 y2 is the membership value 0.4, x1 y3 having membership value 0.2. By this way, we establish a matrix also, and here we are seeing that relationship is between the elements of two universes. So we make the elements as the node of the graph, x1, x2, x3. They are the nodes of the graph. Similarly, y1, y2, y3 are the nodes of the graph, and there are arcs from connecting the different nodes, and we label the membership value on this arc. We are getting this information with the help of the membership value which we obtain from the matrix, relation matrix. Now we are coming on the another topic, that is the tolerance and equivalence property of the relation. We can say, now I am giving you the information to understand the concept of tolerance and equivalence property of a relation. We can see these concept can be understood with the help of three different properties. There are three different properties. One property is the property of reflexivity, symmetry property, and transitivity property. So there are three different property. I will tell you about the property, about these three different type of property later on. But here you understand that suppose we are having three property, and if all the three property has been found in a relation R, in that case that relation is known as the equivalence relation. I'm again telling you, if all the three property has been satisfied by a relation, that relation is known as the equivalence relation. And these properties are reflexivity, symmetry, and transitivity. In the simple way, reflexivity, we can say, suppose we are making a relation from x1 to x1, so there should be complete relationship. If we want to establish a relation from x2 to x2, so if the ordered pair is x to x2, so they must be completely connected to each other. This kind of property is known as the reflexivity. Another, if we are talking about the symmetry, So if there is a connection from x1 xi to yj, so similar kind of connection should be there from yj to xi, right? If transitivity says if we are going from a to b and then b to c, so there should be a path from a to c also. So if these kind of properties have been fulfilled, have been satisfied by a relation, then that relation is known as the equivalence relation. And a relation which satisfy the property of reflexivity and symmetry, then that type of relation is known as the tolerance relation. So it means here you you understand the two different type of relation. One is the equivalence relation, another is the tolerance relation. Equivalence relation are those relations which satisfy, which maintain the three different properties: reflexivity, symmetry, and transitivity. And tolerance relations are those relations which maintain two properties, and they are reflexivity and symmetry. Further, one very important concept is here: an equivalence relation R can be achieved from the tolerance relation by doing the composition operations time and again. And how many times? It depends upon the cardinality of the set on which relation has been established. So listen it very carefully what I am saying. I am saying that suppose we are having a tolerance relation. So I'm saying that with the help of the tolerance relation, I can establish an equivalence relation. So that can only be happen with the help of the composition of the tolerance relation multiple times. So here I'm saying with the bookish word, an equivalence relation R can be achieved from tolerance relation R1 by doing composition operation n minus 1 times within itself, where n is the cardinality of the set that defines R1, right? So see here we are having a relation that is R1, which is the tolerance relation. Rather, we can say the R1 relation satisfies the reflexivity property and the symmetry property. Taking the R1 relation, we can form one another relation, that is relation R, which would be the equivalence relation if we perform the composition operation on R1 n minus 1 times, where n is the cardinality of the set on which relation R1 is defined, right? So now here I am explaining you the three different properties which are very important for us in this lecture. One is the reflexive property, reflexivity, another is the symmetry property, and third one is the transitivity property. So here a relation is reflexive if every node in the graph originates a single loop. Every node of the graph, of the fuzzy graph, they originate a single loop. This has been mentioned here. This is it itself is representing the reflexive property. Reflexivity has been explained here. We are having three different nodes in the fuzzy graph, and they all are having a single loop. It means node x1, element x1 is connected to element x1. We cannot say that element x1 is not having no connection with x1. If it is so, it means reflexive. If it is so, it means reflexive property does not hold. So it means to satisfy the reflexive property, each and every element of a set of a fuzzy relation must have a kind of relationship with the same element. Another, now this is the second one, is the symmetric property. A relation is symmetric if for every edge from vertex I to j there is an edge pointing in the opposite direction. If there is an edge from I to j, so from j to I there should be an edge. It means there should be a connection from j to I also. If x1 is related to x3, if x1 is having some kind of connection with x3, So x3 must have the same kind of connection with x1. So if it is so, then your relation is fulfilling the symmetric property. And if it holds for all the in general it holds, then we can say that relation is symmetric in nature. Now the relation is known as the transitive relation. It means we can say that relation is satisfying the transitive property if for every pair of s in the graph, one pointing from I to j and other pointing from j to k, there is an edge pointing from vertex I to vertex k. Here you can see from 1 to 2 there is an edge, from 2 to 3 there is an edge, from 3 to 1 there is an edge also. You see here, from 1 to 2 there is a connection, there is an arc, from 2 to 3 there is an arc. So transitive, according to the transitive property, there should be an arc from vertex 1 to vertex 3. To see this fuzzy graph here, what is happening? Reflexive property, it holds the reflexive property because all the three nodes are connected to each other. They are having some kind of relationship with the same element. There is the symmetric property also. 1 to 2 there is an edge, from 2 to 1 there is another edge, 1 to 3 there is an edge, 3 to 1 there is an edge, 2 to 3 there is an edge, there is an arc, 3 to 2 there is an arc. So it means symmetric property also holds. And finally we have seen that transitive property also holds. So it means we can say that this fuzzy graph, it holds the third one fuzzy graph, it holds all the three property, and they are the reflexive property, they are the symmetric property, and they are the transitive property. If all the property have been held by the graph, then that fuzzy graph, which is basically a binary relation, that binary relation is known as the equivalence relation. Clear? So it should be clear now that binary relation or the fuzzy graph, they are the same thing. So I have discussed the three different property with the help of the fuzzy graph. It means these three property have been satisfied by the binary relation. So that binary relation will be known as the equivalence relation. Now here we are coming on the fuzzy equivalence relation. Till now you have seen the equivalence relation and the tolerance relation in the context of the crisp set. In the same way, you can conceive the same idea for the fuzzy relations also. So, let R be a fuzzy relation on universe X, which maps element X to X. So this relation R is a fuzzy relation on the element of the universe of discourse X. It is having a relationship on the same universe of discourse. Then R will be fuzzy equivalence if it follows all three properties with reflexivity, symmetry property, and the transitivity property. And according to the reflexivity property, the membership value in the fuzzy relation R in an ordered pair xi to xi, it must have 1. There should be complete membership with the ordered pair xi xi. Suppose there are 5 elements in a set. So first element must have a relationship with the first. Complete membership should be there, right? As we have seen the equivalence relation in the context of crisp set, in the similar way fuzzy equivalence relation also exists. So here we have seen that for the fuzzy equivalence relation, reflexivity, symmetry, and transitivity property must hold. For reflexivity, there should be a membership value, complete membership with all the nodes within themselves. And as far as the symmetry is concerned, so in the fuzzy relation R, the membership value of xi to xj must be same in the same relation within the reverse ordered pair. That is the membership value, that is the connection from xj to xi its value must be similar, must be same as the connection, as the membership value of xi to xj for all xi xj belongs to the universal set X. For the transitivity, let's suppose the membership value of an ordered pair xi xj in the fuzzy relation R is lambda 1, and the membership value of the ordered pair xj xk in the same fuzzy relation is lambda 2, then there must be a connection from xi to xk. So that connection is represented by a membership value, and that membership value should be the minimum of lambda 1 and lambda 2. So by this way we have discussed something related to the equivalence relation and tolerance relation in the fuzzy domain. So that's all about this lecture. In the next lecture, we will solve some of the examples related to the fuzzy relation and composition of different fuzzy relations. So thank you all of this lecture.